Today we're going to be talking about sorting algorithms. And again, we're going to be mostly talking. I'm not going to be writing any code because that's what you're going to be doing in your homework. And it's going to be a bit theoretical, but hopefully you'll get to understand a bit more on how sorting works, why it's limited in some ways, and all those things. All right. First off, tell me what sorting algorithms you have used or you know and why you've used them. Anyone, go.
Quicksort, merge sort, because they are fast.
All right. Which one of the two is faster?
It depends on the problem.
It depends on the. This is a great answer. This is an answer which we'll be using a lot today. It depends on the problem, and actually, it depends on. In this context, the problem is the numbers which you are given, their format, and their initial state. Okay, good, great answer. Anyone else? Any other sorting algorithms?
Radix sort.
Radix sorts. Okay, that's even faster. Some would say. Okay, we're gonna get to that. But is radix sort? I mean, when did you use radix sort, and what are its limitations?
I think that the only limitation that it has is the space it uses for sorting.
Okay.
Because it actually kind of works like a sorting network.
Yeah.
Using the queues for sorting from the most significant digit to the less significant digit and the other way around.
Yes. Okay, good. Right, so then let's create a table. Okay, this is not what I wanted. There we go. And here we're going to be splitting it in a few segments. I think 1, 2, and 3 segments, I guess. Okay, and we will name these segments pretty good. Actually, pretty bad, the first one. Pretty good. And these ones will be amazing, but with caveats. Oh, I hope I spelled this right. I did. Okay, so we're going to be skimming through a few sorting algorithms. And let's just start off with the most basic one. I think you've learned this first in high school, which is bubble sort. And can anyone tell me what the complexity of bubble sort is?
N squared.
O of n squared, yes. Now, what is the basic approach of bubble sort? Anyone? Well, how does bubble sort work?
We start from the beginning of the array and then switch all the elements that is greater or smaller than the current element. And we do this pass in the worst case n times.
Okay, yeah. So basically we switch pairs. Switching pairs, and importantly, consecutive pairs, right? If needed. All right. Okay, this is bubble sort. Let's go on with another well-known one, insertion sort. What is the complexity of insertion sort? Anyone?
Is it also n squared?
Yes, it is. So it's still O of n squared. And how does this work? Can anyone remember? No one? Come on. I'm sure you've implemented it.
We iterate n-1 times through the array, and we always take on the ith iteration the ith element, and we swap it with the element in the left to it if it is smaller than it,
Okay.
as long as it is smaller. So we swap more times per iteration.
Okay. So basically, at the ith iteration, is there anything you will know for sure in insertion sort?
The elements left to the current element are already sorted.
Right. So after the ith iteration, the first I elements are sorted, correct? They're not, I'm not taking into consideration the whole array sorted, but the first I elements of the array are sorted. Maybe there are some elements which are smaller, and then they will basically be shifted by this insertion sort at the beginning of the array. But yes, that's the invariant here. Okay, and the last one would be selection sort. What is the complexity of this one?
It's also n squared.
Yes, correct. And how does it work?
It kind of works like insertion sort.
Okay.
But it selects an element and it it's putting in it first.
Go on.
It's hard. It's replacing it like a certain element with the element in which position it should be sorted.
Okay, and more simply put, basically it just always at every step, it finds the minimum element and then puts it in the right place. So for example, at the first iteration, it will find the minimum element of all the elements, so all of n elements, and then put it at the first position. And then it will search the minimum elements of the remaining n-1 elements, and then puts it in the second position, and so on and so forth. So after the ith iteration, we can know for sure that the first I elements are in their final position. It's not even that they're sorted, but they're in their final position. All right, so these are the, well, pretty bad sorting algorithms. There are maybe a few more, but these are the basic ones. And they're pretty bad because of their complexity. All three of them are actually O of n squared. And we'll be comparing a few numbers so that you'll understand better why O of n squared is so much worse than all the other complexities, which we'll talk about in a jiffy. Okay, so let's go to pretty good ones. And they have already been mentioned. The first one is merge sort. And what is the complexity of merge sort?
N log n.
Yes, it's O of n times log of n. All right, and how does merge sort work?
Using the divide and conquer concept, so we would divide our array into two subarrays, sort each of them, and then merge the two resulting arrays.
Okay, good. So basically, we divide our approach in halves, and then work on the halves, or keep on dividing until we reach a let's call it a comfortable size, at which we actually implement a one of the three, and it's usually insertion sort algorithms, and then we we put everything and we trickle back up our results and merge our sub subarrays. So let's actually, should we make, no, we're not going to make an example right now. There are many examples on YouTube on how this works. But no, what we're going to be talking about today is mostly complexity and the cases in which you should use them. If you are not sure on how it works precisely, just YouTube it. There are so many examples on this. There are even Hungarian dancers who exemplify on stage how all these algorithms work. You have no excuse if you don't know them by now. And until next time. Okay. So yes, it's using divide and conquer and basically just halves everything until we get to maybe size 2 or 4 in our subarrays, and then we sort them. And then once they're sorted at the last level, we then trickle them up, and we basically concatenate the subarrays, but of course we make sure that they're concatenated in ascending or descending order. All right. And then there is one more here, which is called quicksort. Now, what complexity does quicksort have?
Also n log n.
Also n log n. O of n times log of n. And how does this work?
It first it picks an element like which is the pivot of the array, and then position all the elements smaller than the pivot in the left side and the elements greater than the pivot in the right side. And then recursively it calls itself for the left array and the right array.
Yes. Elements bigger than pivot on its right side, and apply recursively to halves. Well, actually 2. Anyways, yes. Now let's talk a bit about this. The most important thing here is picking that pivot. There are many ways in which you can do this. Some are great, some might fail, and we should investigate that a bit. How does one decide which pivot to take? First of all, the question should be, what could be the best choice of a pivot? Taken into account that every element which is smaller than the pivot goes on its left side, and then every element which is larger goes on the right side. What is the best choice for a pivot?
A median.
The median. What is the median in this case?
It's the element that is like the most the closest to the mean of all the values.
Yes, correct. Now, is there any way in which you can find this median value quickly in an array of unsorted numbers? What is the quickest way to do this? Hello? Anyone?
The crude approach would be to sum all the elements, and then after computing the mean, we try to see which number, again, searching from the array, to see which number is closest to that value.
Yeah, what is the complexity of this?
I think it's n.
Yes, it is O of n. And regardless of how you put it, the solution will still be O of n. Okay? So that's the best case here. But if you decide to put an operation which takes O of n inside this quicksort, just when picking the pivot, you will see that its complexity changes from O of n log n to O of n squared. So we can't do that. Even though that would be the best solution for choosing the pivot, we can't do that. So any other solutions? By the way, am I the only one who hears that sound? It's like a very high-pitched sound.
I also hear it.
All right, okay, so it's not from me. All right, so any other ways of choosing a pivot? Come on.
I have one question regarding the previous approach.
Yeah.
We said that we want to choose the median for the pivot value, but is it sure that the value which is closest to the mean is the median? Because
well, theoretically, yes, but of course, there are some exceptions. I mean, basically,
in most of the cases it will be, but in some cases
yes,
it may be really far from the.
Yes, you are right. You are right. Basically, the median in this case should be interpreted as the value which has as many values to the left, if chosen, and as to the right, based on this approach, like putting elements which are smaller on the left and larger on the right. You are perfectly right on it's not an average, because that would be the previous definition, but it's actually the median value. So it's not always going to be necessarily, and you are perfectly right, the closest element to the average. It's actually going to be the element which has, in this context, in the context of this array, as many elements which are smaller than it as bigger. Okay, does that cover the problem?
Yes, it does.
A bit. What do you mean a bit?
I didn't say a bit.
I'm sorry.
Yes, it does.
Yes, it does. Okay, now, okay, fine. Good. Now, come on. Give me other ways in which we could be dealing with picking up pivot.
It might be risky, but we can take the middle element, the one with the middle index, and then go from there.
Why risky?
Because it's not. We can't trust it being close to the average.
No, we can't. And actually, we don't need to trust that.
So, how would that work? I mean, my logic was that if we take that, we have in the array not really sorted, but we have as many to the left as many as we have to the right, and then we just go recursively and sort them 2 by 2.
Yeah. Well, it's an okay approach. It's an okay approach. I think it's as okay as picking it randomly. Okay. Now, another solution to this, and this is maybe a bit more widely used, is the median of 3 pivot. For example, you don't take the median of all the values in the array, because that's going to take O of n, but you take the median of 3. And for example, you can take these 3 values as being the first, the middle, and the last element, and then you take the median of that. Okay? Basically, once this algorithm runs a few steps, you'll see that the subarrays which are created are going to be nearly sorted. They're not going to be perfectly sorted, but they're going to be nearly sorted. And because they're nearly sorted, that gives you, if you're going to choose a median of 3, chances are that it's going to be a good enough median value, a good enough pivot. Okay, so this is maybe one of the most widely used techniques. So I'm going to write it down. And maybe big pivot either randomly, or actually the first one was median of all values, best result, slowest result, median of 3 values, which is on average great result, fast result. And there is another one, which is either going to be taking middle element or taking a random element, which is on average, it's still great, or maybe just good result, fast result. I couldn't really, I mean, you'll compare them in your homework, but that's something else. Anyway, taking a random element, I want to talk a bit about this. What is the worst case scenario for picking a pivot?
Picking the smallest or the largest element.
Yes, why?
Because then we decrease the length of the subarray that we want to sort afterwards only by 1.
Yes, correct. So if we are unlucky enough to pick the largest or the smallest element of the array, our sub-problems, our subarrays, the ones which get divided recursively, or well, iteratively, doesn't really matter, below, are only reduced by size of 1. And what happens if at every step we are unlucky enough to pick the largest or the smallest element of the array?
It's a selection sort, basically.
Yes. It basically transforms into a selection sort, and that will give the complexity of O of n log n, of O of n squared, I'm sorry. Now, if we are to pick a random element of each time as a pivot, what are the chances that this random element is always going to be smaller, the smallest or the biggest? Anyone?
2 over n.
2 over n? I would say it's not 2 over n.
By random, do you mean that we, at each step, we choose a position at random?
Yes,
or
yes,
that,
yes.
Okay.
Yes, exactly. A position of the subarray at random. Mm-hmm.
Is it to the power n over n factorial?
Yeah, it's roughly that. I mean, there are a few nuances here, but roughly speaking, it's 2 over n factorial. Those are the chances. So imagine having an array of just 15 in size. Okay, so let's see how much is 15 factorial. 15 factorial is already a lot. Do I have a calculator for this? 15, and where is the factorial? So 15 factorial is 1 trillion 307 billion 674, actually, yeah, 1,368,000. That's 15 factorial. That is a large ass number. And well, the chances are that if we have an array of size 15, if we randomly choose the pivot at each step, the chances that it will be the largest or the smallest at every turn will roughly be 2 in 1 trillion. And that's size 15. You're going to be mostly dealing with a lot larger sums than this. So just FYI, if any problem is taking a factorial complexity, is having a factorial complexity, if any solution has that, it's a shitty solution. By all means, it's a really bad solution. So factorial solutions are really, really bad. And even exponential ones are bad, but factorials are even worse. All right. And so this was about it for quicksort. Let's go on to two more things here in the amazing category. And the first one was already mentioned, and it's called radix sort. Now, first off, what is the complexity of radix sort? Anyone? No one, really.
It's n times a constant.
What is that constant? Because we know what that constant is.
I think, if I remember correctly, it's the recursion levels.
No, you're not going to be having a lot of recursive functions in.
Or it's the number of digits.
Yes.
Okay.
Yes. Where n is equal to number of numbers, whatever, and or maybe just size of sorting array, and where k is equal to the length or the number of digits.
The magnitude of the number.
Yes, the maximum number of digits which a number has. And by all means, this is a great complexity, okay? It basically, it's just O of n plus a constant value, which you can compute beforehand because you can know how large the largest number is. This is great. Okay. So when can't you use radix sort? Anyone?
If I don't know anything about the range of numbers that I need to sort.
Yes. So that's a good indicator. Yeah, that's a good indicator that you might not be able to use radix sort. Okay. Let's move on to the next one, which is counting sort. Count sort. And did anyone ever use this?
No.
Really? Huh. Interesting. Okay. Well,
not for sorting purposes.
Yeah.
I used to watch some videos about sortings, but I don't think I saw this one, or I might have not paid attention.
So basically what this does is from the array which you want to sort, you create a frequency vector, okay? And you increment at each position, you increment that number or that position starting from 0 each time you find that corresponding number in your array. So for example, if your array looks something like this, then first off, you would need to allocate as many, an array of size max of these numbers. So I need to allocate an array of size 7. So initially I will have something like this. 1, 2, 3, 4, 5, 6, 7. And at the end, basically, again, I skim through all of these and increment the position at which they correspond. So I don't find 0 in my array, but I find 1 twice. And then I find 2 0 times. I find 3 once. I find 4 once. I find 5 once. And I find 6 once. And actually, I don't find 6, and these should be 1. And I find 7, and this should be a size 8. And I find 7 once. So imagine something like this. 0, 1, 2, 3, 4, 5, 6, 7. So again, I find 0 0 times. I find 1 2 times. I find 2 0 times, blah, blah, blah. And basically this counts, and this is a frequency vector. It counts how many times my elements are found in the array. And at the end, when I generated this, I can simply print them out in order based on how many times it appeared. So 0 doesn't appear at all, so I don't put it. And then I have 1, 1, which appears twice, and then 2 doesn't appear, and then 3, and then 4, 5, and then 7. Okay, so this is counting sort. Basically, counts the number of times each element appears. And this looks great in theory. This is like the simplest kind of sort. But what is its limitations? Anyone?
I think it's again the range of in which the numbers are. If you don't know the range before that, we can exceed the space of the frequency vector.
I may also need a pretty huge array for the frequency map.
Yes. So if, for example, you would have a very large number, even just one very large number, and all the other numbers are very small, in the range of maybe 1 to 100, you will have to allocate as much space, as many elements in the array as that number, that very, very large number. And in case that's in the realm of maybe millions, and it's not unreasonable to think that you might be sorting a number which is 1 million or 2 or 5 or 6 or 7 or a billion. It doesn't matter. It's not unreasonable. You can't allocate an array of that size. I mean, you theoretically could, but I mean, it's not practical at all. So counting sort works best when, as you said, when you know in advance that you'll be dealing with mostly small numbers. So if you know that your numbers are in the range 0 to 100, counting sort works wonders. It's really fast. Its complexity is like O of 2, I think. No, actually 3. Because first off, you go through everything to find the maximum value, you allocate that space, and then you go through everything again to create your frequency vector, and then go through that frequency vector to just print out the result. O of 3, that's it. That's really convenient. That's constant time. And these amazing but with caveats methods are just that. They're amazing as long as some conditions are met beforehand. All right. Now, any questions so far? No questions. Everything was sparkly clean and clear. Great. Then I have a homework for you. I couldn't find the time to check the homework which I gave you last time, but I promise I will. So your homework is something like this. Pick one of each category of sorting algorithms. Implement them, count number of comparisons, actually count the number of actions in which they comprise of comparisons, and basically attributing, what is the term in English?
I think array accesses or something like that, accessing the arrays.
Yes, but more general. Comparisons and assignments. And accessing array, no. Should you count that as well? Yeah, actually, yes. So if you are doing a comparison equals one action, then assignment equals also one action, and then access equals one action as well. So you sum them up, and you should print them out independently as well. And then you'll see, and I have to close this meeting, but we'll end it here. You'll see how much better a merge sort or a quick sort is than a bubble sort. And then again, how better a counting sort or radix sort is than all the rest. Okay? Okay, let's just stop here, and I'll tell you more about the tests in writing on WhatsApp, okay?
Okay.
All right. All right, take care.
Bye.
Bye.
Bye.